Okay, we have here another integral from MIT 2025 semifinals, round one, problem two. We have the integral from minus pi to pi, natural log 82 plus 2 cosine x, square root 81 minus sine squared x minus 2 sine squared x dx. Okay, I definitely feel like we need to factor this somehow. It's not really clear how it's going to work because it's such a mess, but I think that's going to be the starting point. The first thing I can do, one minor thing, is we've got our bounds symmetric around 0, and this is actually inside here. Well, actually, the whole thing is an even function, just because the sines are squared and cosine is even. So for an even function, what I can do with symmetric bounds is we can just change the lower bound to 0 and bring a 2 out front. And then for the factoring, the interesting thing here, it's pretty strange having 82, but it's only one off from 81. I think what I can do is, for 82, I can write that as 81 plus 1. Over here, we've got two copies of sine, or sine squared. So I can kind of break it up like minus sine squared for just 2 sine squared. And then I can kind of regroup it because I can put this 81 with this, and then I'm matching this. So I kind of create 81 minus sine squared. And then kind of reordering it. I dropped the ln for now. We're just dealing with the algebra of this. We have, I can take this one, plus 1 minus sine squared x. Let's put those two together. That seems convenient to do it that way. And then we have this last term, which is going to be this plus 2 cosine x with the square root of this stuff. But then 1 minus sine squared x, that's the same thing as cosine squared x. So let me fill that in right here. So I don't have to rewrite everything. We'll just plug in cosine squared x. And now I think this is ready to factor, but I want to put some labels on things just because it's kind of messy the way we have it. So instead of dealing with cosine, let's deal with, we'll call cosine a. So this thing here is actually a squared. And then this thing right here, which is the same as this, we'll call b. So let's see, if that's b, plus 2 times a square root of b. Putting labels on things doesn't really do anything. It just makes it easier for us to see it. I feel like it's just easier to factor and probably less writing doing it this way too. So then what happened is now, it's still a little weird, but what we have here, this can be written as a plus square root of b all squared. But now remember, we're inside the natural log. So let's just throw the natural log on here. I know it's not equal to this, but if I put the natural log back, then we've got log properties. And so then we can write this as 2 ln a plus square root of b, but let's plug back in right now. So a is cosine x. So what this is going to look like, 2 natural log cosine x plus square root of this thing, 81 minus sine squared x. So we'll take this thing right here, throw it back into the integral, and keep going from there. Okay, so one thing I should mention, when I plug this back in, we get the 2 out front as a constant multiplied by the 2 in front. That's how I get the 4 in front of the integral. And now for the next step, it's still pretty gnarly, right? I don't really know how to integrate that. I suppose you could try integration by parts, but that looks like a mess. So I'm not going to do that. What I want to do instead is King's principle. It's not really clear that it's going to work right away, but the giveaway is kind of the bounds, trig functions, natural log. There's a few things there that make me think it's going to work. Also, when you plug in, for King's principle, like what we're using is our bounds, right? We call the bounds a and b. And if this is our f of x, what we're going to want is f of a plus b minus x. But in our case, adding the bounds, subtracting x, we're just looking at f of pi minus x, which tells me we're going to be able to use complementary angle formula on cosine and sine. So the thing to know for this is cosine pi minus x is just minus cosine x with the supplementary angle formula. And then for sine, you're just going to get back sine x when you do this one. So using that King's principle is going to be real easy. We keep our bounds exactly the same. We get something really similar. We just get a minus sign on the cosine. So we have natural log minus cosine x. And then this piece is going to be exactly the same as we just get back a sine. And then now what we can do is we can put some labels on our integral. I guess we could even do our original integral. So for our original integral is I, that's going to be our goal. We can call each of these I, and then just add them both together. When we do that, we get 2i. Because we have the same bounds, I'm going to put them together in one integral. We can kind of factor the 4 out front. And then we're integrating from 0 to pi. But But I'm going to kind of save a step here. Instead of writing this out, we're adding two natural log terms. If you have natural log of a plus natural log of b, that's just the same thing as natural log of a times b. So what that allows me to do is put this together in one natural log, multiplying these out together. And what you're going to have is like a difference of two squares. I'm going to reorder it. So first I'll multiply this times this, and we just drop the square root, and we get 81 minus sine squared x. And then for multiplying the cosines, we're going to get minus cosine squared x dx. But right here, we're really in luck because all I need to do is factor a minus sign out, and we get minus sine squared x plus cosine squared x. So this piece right here is really just minus 1. So plug that in, and that's going to really solve it for us because now this here is just going to be 81 minus 1. And that's just 80, so, and actually that's just 80, which is just a constant. So I can just go ahead and integrate this, but before I do it, let's actually divide off 2, just because I want to isolate the goal of I. So when we do this, we're going to have, now we have a 2 out front, ln 80 is a constant, integrate, we just get an x, and we need to evaluate from 0 to pi. So evaluate it at pi, and for my final solution on this, we just get 2 pi ln 80, and that's it. Okay, there you go. Good one from MIT 2025. Thanks everyone for watching. Have a good day.